Okay, there we go. Right. I guess that USB port isn't working today. Fantastic. Thank you very much for pointing that out. I actually just noticed myself about 10 seconds before you posted, but thank you very much for pointing that out. Yes, so, any case. Yesterday we started implementing some functionality where, given a point in 3D space, we can find the closest point on the nav mesh. And the idea behind that is, if we say drop a character in here, we need to, we need to find somewhere practical to put them. At the moment, it seems to be nearly working, but it seems to be sometimes just choosing really strange kind of, I would expect this to almost always be going straight down, but it's not. It's kind of jumping around all over the place. I have had a thought on what this might be, and yep, to reuse that old joke, it definitely hurt. So at the moment, we are, we're prioritizing triangles that are beneath us over ones that are above us, and we are then picking the closest one. However, there's another thing we should probably be doing, which is we should probably be prioritizing triangles we are directly over. If we're not over any of the sort of boundaries, that should be one that we're prioritizing. So, I'm going to add that as a new prioritization. And let me just go to base sprite. We're going to have a bit of a think about this. If I grab the line tool, let's say we've got a triangle here, right? So we're looking from the side, and we've got one here, right? Let's try and think about how the prioritization should work here. So if I'm here, right, I would expect it to kind of prioritize, downwards, not upwards, right? And again, if I was here, I would expect it to kind of prioritize that way. However, if I had two triangles, right, one here and one here, I would expect it to prioritize this one over this one because it's quite a way sideways from there to there. So what we have here is ones that are below should be prioritized above ones that are above, but after that criteria, ones that we're kind of over should be prioritized over ones that we're not, even if the ones that we're not are closer, because we're kind of falling onto the triangle. So, we're going to need to add a new Boolean here to track that. Just go through, and every time that we discover we're over a wall, we say that we're not over a wall. Might also have written the logic slightly wrong for this. So if we're above, or the closest point isn't above the triangle, and within the walls, or no, it was right in the first instance. Okay, so if we are above and the previous point was below, okay, and we are within the walls. Hang on. So if we're above or previously below, right, and we're within the walls, or we're previously outside the walls, hang on. Okay, all right, okay. So I'm trying to get this logic into my head. It's a bit too early for this, I think. Okay, so oh my god, my brain is melting. Uh, Hang on. There's actually okay. The complexity here is actually three states, right? So if we I need to write this as a sequence of statements, I think. So if we're below and the closest point is above the triangle, then we just skip this we skip this triangle on the basis that there is no way that we are in a better state. Oh wait, we're already doing that right there. Okay, all right. Oh, maybe I need to early exit here actually instead. Right, so oh my god, this is a lot of Try to keep all this in my head, I'm just losing it. Okay, right. A great state of mind programming. Right, okay. Let's draw that again. So we've got kind of like three lines here, right? Our point is here. So let's say that for the sake of argument, actually let's draw a couple more as well. Let's say for the sake of argument, right, we're sampling a point here. And let's say that we had previously sampled this one on the right, and we've gone like, hey, you know what, this isn't ideal, but at least we're kind of, we're above it, so it takes priority over these two. We're outside the edge. But then you realize this one's here. In which case you need to go, well, even though we were closest to that one, and we're above it, we need to prioritize this one. Okay. Right, so this starts getting really complicated. So we actually got like three levels of things that can all kind of impact onto whether or not you prioritize this triangle over the one you've already got. So I might invert this. At the moment, this is getting really confusing because I have something saying above and something saying below. Okay, so if we're above, or the closest point was below the triangle, okay, then we carry on. And then if we cross a wall, and we probably get rid of this within walls entirely. So right, okay. So we only consider whether we're within walls if our above state matches the above state of the previous triangle, because otherwise... Okay, right, okay, there we go. That took way too long to figure out. So if we are above the triangle and the previous triangle was above the triangle, and closest point within walls. There we go. My god, that took way too long to get my head around. I definitely am not in the right state of mind for programming today. All right. So we go for all that, and at that point, the only thing we need to consider is whether the distance is closer. So now we can just record that. Why did I ever make that inverted? That makes no sense. And we still need to record whether or not we are within the walls, because we're going to be saving that when we finally get to the bottom. Man, it's got really complicated for what was originally just going to be a distance check. Okay, let's build that and see whether what comes out the other end makes more sense. I'm praying it does. I don't know if I can take another debugging session on this. No, it's still doing things that make no sense. Ah! Oh, and then it froze. Very good. Oh, there. Yeah, so it's still kind of jittering around all over the place. Oh. I really regret actually testing this, to be honest. I should have just left it broken and then just gone, it's probably fine. I probably wouldn't have even noticed if this was just broken. Okay, so next thing I'm going to do is I'm actually going to draw a line to the sky. And the reason for that is I just want to see whether this is going straight up or not. Hang on. I just realized where I might be going wrong with this. Because I'm using the distance on this axis. You know, I should really be going straight down, shouldn't I? That would make way more sense. I should be getting the height of this triangle at the point we'd theoretically be landing on it, not the distance along the normal of the triangle. Okay, so how do we get that? Well, I guess what we'd do is we'd project this point onto this. Right. And then we take the difference along that axis. Okay. All right, okay. That might actually be a bug. Maybe. I hope it is. Okay, so just thinking about how I best do this. No, actually, that shouldn't be causing this bug at all. Let's just draw another diagram so you can figure out what the heck's going on here. So we have this and this, like this. A super exaggerated example, right? We've got a point here. We'll say like here. And we've got distances to there and to there. Would we be expecting like any chaotic effects as it kind of like, you know, say arcs around like that? Not really. Still, it probably would be better if it just went straight down. That would probably produce an effect more like what we're actually after. And the question is, though, do I actually want to introduce a dependency on gravity in this? Because you might be using this in situations where there is no gravity. Like that was completely wrong. Whatever it just did there was completely wrong. Okay, let's just double check what we've just written because it might still be wrong. So yeah, if we're above or if the closest point is above the triangle, okay. Right, okay. Oh, wait, hang on, we need to skip this if any of these are met. Oh, hang on. Hang on. Hang on. Hang on a second. Okay, so if we're on the same plane and if okay, all right. That might work. Just keep poking at it until it does something that looks right. That's how we do things around here. That still doesn't look right. Does it at least kind of like not flicker about? Oh no, it still flickers about all over the place. Oh, why is it doing that? Why is it doing that? Ah. Too ill for this. Okay, so if we're on the same kind of level as what's already there, and we are further away, then skip. Otherwise, they're saying that let's just go first and try and figure out what's going wrong here. So if we're above and the previous one wasn't, then continue. That makes sense. If we're within the walls and the previous one wasn't, then continue. Right? Because if we were outside the walls and the previous one wasn't, then we'd quit out. So yeah, that kind of makes sense. This should be working. Okay, all right. So I guess the next thing we can kind of do is, I'm just going to just reduce this to a single triangle and see what happens. See if I can figure out what the heck is going on here. Oops, no, not every object, just that one. Nav meshes. I had anticipated this being a stream and a half, and so far it's taken like 5. It's definitely a developer estimate then, isn't it? Hey, hang on. That's not constraining to the edge of the polygon properly. What's going on there? All right, okay, so we're getting a constrained point. Yeah, we're definitely doing that. And then this should this should be working, right? Because yeah, we're performing a dot product between the distance, so the difference between our point and one of the vertices on the edge, where we've checked that the normals are correct because we can see they're pointing over the edges. Yeah, that's right. We're getting the dot product, so we're getting how far we are over that edge. And then if we are over that edge, we are then multiplying how far over it we are by the normal. It should give us a vector of exactly how far over the edge we are in which direction. We are then subtracting that from the point, which should put us back over the edge. Right, okay. And then we're doing the same thing for the second vertex. Yep, that's good. And we've got the edge normal, and we're doing exactly the same thing again. So, why doesn't that work? Huh. Huh. Okay, question number 1. Is it actually hitting this at all? Because it should be, but maybe it isn't for some reason. We can see that it's definitely selecting the triangle because it's definitely drawing a line to the surface of the triangle. Wait, that edge works. That edge works. And that edge looks like it's working. Huh? But then when it crosses more than one... Oh, hang on. Hang on a second. Oh, I know what it is. Let me draw it. Let me draw it. Oh my god, this is so dumb. So, okay, we've got a point, right? Oh, we've got a triangle. We've got a point here. Right, so we've got this edge extending out to here. We are then projecting this onto here. Right? Okay. We are then projecting it back into... Hang on, I need to draw a better example of a non-right angle, I think. Let's try something like that. Let's try something more extreme, like say that. Okay, so we've got a point kind of here. Okay, we are projecting it onto... Actually, let's try the other side. We're projecting it onto here, right? But then we're projecting it onto here. Now in that case, that actually kind of worked out. However, if I did it on this side, right, we end up projecting it onto here, and then... Oh, it wouldn't be over that edge. What is happening here? This doesn't make any sense. Okay, let's try a point in the middle. So, yeah, it projects it onto that edge. Okay, and then it sees it's still over this edge, so it projects it onto... And that would still work. What's going on here? Okay, Right, okay, all right, okay. Let's, Huh. Something's definitely going wrong. I'm just going to do another check on here for a last line effect, because I've just drawn it and I couldn't see a point in a case in which this wouldn't work. Let's also just have a look at which edge it's actually... It seems to be just this corner that it's having a problem with, right? Yeah, that's the one that seems to be able to fly off. So that's going to be the only... Well, it's going to be a vertex that's kind of like positive on the x-axis relative to the others. Oh, it's also happening on that edge. Huh, okay, all right. Okay. Oh no, Okay. So what I'm going to try here... What I'm going to try... is I'm going to specifically detect the corner cases. Right? Right, okay. This is getting complicated. Very good. Okay. So if we're over CA and we're not over anything else, we can put that in there. And if we're over BC, and again, we're not over anything else, we can put that in there. However, in these cases, we need to instead just hard lock it to the corner. And let's take the logic I just wrote for this and kind of replicate it down. We're going to solve this puzzle. We are. It's going to happen. We will overcome this nightmare I've just made. Okay, so if we're over AB and BC, that must mean that we're at, that must mean that we are at, yeah, B, because it's the only one common. My God, my brain's just not working today. Okay. So we're going to copy B to the constraint points. Wait, I pasted that into the wrong place. What am I doing? Okay, so if we're over CA, that means we're at A. And if we are... Oh, do I never retrieve A? I guess that makes sense because, yeah, I did that thing where I reused the other points. So we need to see where we're fetching. There it is. So I can just use that here, just directly use the vertex. Very good. And we can calculate whether it's within the walls by doing, it's not over AB, and it's not over BC, and it's not over CA. Helps if you name your variables, doesn't it? Yes. Okay, does that work? Does it even compile? Oh yeah, it does, okay. That's me worried. Wait, what? It still escaped. What? How did it escape? Huh? What? What? How is that even possible? Okay, let's just double check what I've just written. Okay, if we're over AB and we're over BC, then we're at B. If we're over AB and we're over CA, then we're A. Yep, okay. Otherwise, project it onto... Oh, I'm not... Wait, hang on. Let me just take a copy of that and just undo everything I just did. I just noticed something. And if this is what the problem is, no, hang on, that's fine. Right, yeah, I'm writing to that there. I'm not reading from it. I was like, do I never write to this? And it's just got random garbage in it, but no, we are writing to it right there. Okay, so in that case, we're over AB, so we take the distance to AB, take the AB edge normal. Yep, that's fine. If we're over BC, B edge normal, distance to BC, that's fine. And if we're over CA, again, that's fine. That should be working. Why isn't it working? Ah! Okay. All right. Don't go insane. There is a rational reason why this is acting irrationally. You will find it. Probably. Or you'll go insane. One of the two will happen. Okay, let's have another look at this. It's almost like it's not realizing it's over this top line. So let's have a look at the movie theater. What is the geometry of this? So let's just draw a little diagram of our triangle here. So it looks like, given that one's all the way over on the right, it looks like that one's A. And then we have two triangles, and it looks like it's built like this. Well, but I'm both going to go insane and solve this. I mean, probably, yeah. So it looks like the problem is happening on this line. So sometimes it's seeing that we're over this line, but it's not seeing that we're over this line when we're up here somehow. Now we know that the coordinates and the normals are good because we can see them and they look fine. Oh, I just did the opposite. That just saw we were over, what? That just saw that we were over this line, which is AB, and not this line. Okay, all right. Ah! All right, okay. Let's see here. So we're over AC and we're over AB. So it should have gone down to, it should have gone to here. Yeah. And it should have gone, you're not over BC because you're nowhere near it, but you should be over CA, in which case it should be copying the first vertex in. So for some reason, it doesn't think it's over that edge. Why not? Why does it not think it's over this edge? What is going wrong here? The normals are good. We know they're good. We're subtracting the point from one of the 2 points on the line. Yeah. And we're writing that to our difference variable. We're then performing a dot product, and that the normal should get us the distance over that edge. Okay, so I'm going to do a bit of hacking here. I mean, that probably shouldn't surprise you. Let's just open Blender and let's find the point. So it's like there-ish, right? Let's hard lock it to that exact point. Yeah, so rather than doing this, we're going to hard lock it to a point that we know reproduces the issue, because then we can start putting in, so we don't have a debugger that we can really use here to really tell what's going on. Yeah, so if I do that and run it, it should, okay, that's not a point that reproduces the issue. Okay, let's try pushing it back a bit further. Let's see if we can find the breaking point. Okay, there we go. For whatever reason, that point doesn't seem to think it's... Yeah, for whatever reason, that point seems to think it's over this edge, which is AC, but not AB. So let's just verify that. So, sorry. Yeah, it thinks it's over AB, but not BC. So let's just check that. Indeed, it doesn't think it's over that edge. Huh. Now, we know the normal's facing the right way because we can see it. Let's have a look at this point in 3D. So we've got our advance here, which is, yeah, I think we just added, yeah, added one to that. Oh, hang on a second. It's actually not over that edge. Okay, that's actually correct, but the thing is, it's kind of projecting this way, not to sort of here. Oh, hang on. Projecting onto this edge. Hang on. Projecting onto this edge actually moves it over that edge. Okay, right, let's draw this up again. So we are here, right? And then projecting it onto there means it's now over that line. All right, how the heck do we solve that? Hmm. Huh. I don't remember having this issue. I've implemented this before. I don't remember having this issue. Maybe I didn't test it rigorously enough. Okay. All right. Okay. Okay. Don't go insane. Don't go insane. Don't go insane. How the heck do you detect this? I don't want to just iterate like multiple times. It feels like that's just a hack that will probably have problems. Um, but maybe I do. Yeah, okay. All right, okay. That's what we're going to do. We're going to iterate twice. I think twice is always going to be enough. I can't see a case in which that wouldn't be enough because you only got that you could only really be crossing like two edges. I mean, you know, if say I projected onto this point here and then oh no, no, that would then be over this line. And you would like have to kind of bounce back and forwards and see, oh my god. No. Ah. Oh my god, I'm losing my damn mind. Okay. Uh, okay, there has to be a better solution to this problem than what I'm currently doing. There has to be. But at least now I know what the problem is. At least I've got like an idea of why it's doing this weird behavior. Hmm. So I guess, hang on. I checked for the first edge and, right, okay. Okay, so here's the deal, right? I checked it's over this edge and we find out, yes, it is. We then check if it's over any other edges once we project it onto that point. And if so, we go into that corner. So for example, if it ended up over this edge as well, we go into this corner. Okay, okay, all right. Worst case scenario, we end up in a corner that we shouldn't be in or something, I don't know. Right, okay. Okay, all right, okay. All right. So we can cut basically all of this out. And all of this can go pretty much. Okay, all right. So we're over AB, let's get our AB projection code. Yep, that works, that's the one. So yeah, we project the points onto that edge. And now we just need to check whether it's over either of the neighboring edges. Okay. Just gonna make a to-do to do that. Okay, all right. Right, okay. Now, there's only one case in which we are within the walls, so I'm going to make it default to false and set it to true if it manages to get past all of the walls without finding something. That should work. And then this is BC, so you're going there. And this is CA, so you're going... You're going there, and that should actually be down there. Okay, so we know we're not over AB by this point, so we only need to check. Hang on, so we're on BC here, C, yeah. We only need to check at that point one more edge. So this is starting to get complicated, but it's a complicated we can handle. Okay. Let's go comment all of this out. And we no longer need to do this because we've made a record above of whether we're over walls or not. Okay. So next up, we need to basically replicate this code here. And yeah, if we're then over that wall, then we need to do B. Otherwise, we then need to compare with CA, which we've got code for down here. Okay. And then, do you remember when I thought this would be simple? Do you remember when I thought this was going to be easy? Ah, what a fool. What a fool. Okay, so this is putting us in point B, which is that. And then we need the code to put in... It's never simple. You are right. You are completely right. And we never actually access vertex A as a result of all this. That's kind of interesting. We've managed to basically do collision with a triangle without reading one of the vertices. I mean, we've got things computed from the vertices, but... Oh no, we're missing a bracket somewhere. Oh no, oh no. Okay, let's try and figure out where it is. Okay, I'm going to put one there, see what happens. Let's make sure that our loop's ending where it's supposed to. Ah, hang on. No, that bracket was not supposed to go down there. It was not supposed to go down there. So, okay, what do we have here? So, yeah, so if we're over AB and it's bad, that's fine. Otherwise, project onto line AB and then check whether we're over BC. If we are, then go to point B. Otherwise, check whether we're over line BC. And if we are, go to C. Okay. Otherwise, look at edge BC. If we're over it, then check whether we're outside, that's fine. Then check whether we're over line CA, and if we are, go to line C, that's fine. Let's try and figure out where this missing bracket is. Okay, otherwise, we're checking line CA, so grab okay, I think there should have been a bracket there. Because that would take us all the way up to there, which is probably fine. That doesn't look right, but it looks less wrong, if you know what I mean. Okay. That looks like it's, I've unfortunately got the same color at the end of the line as I've got there, so I'm just going to change that up a bit. Let's change it from blue to magenta. See how that looks. Okay, yeah, it's definitely going to that corner, whereas it should be going to that corner. So that corner is A. So you know how I just said it's kind of weird how we don't read from A at any point? Yeah, I thought it was kind of weird, to be honest. So let's see here, what we're doing wrong. So we're over AC, okay. Oh, no, hang on. I've tried to optimize here and I've made everything worse in the process. Okay. Right. Yeah, because I was like, well, you know, if we're over BC, I don't need to check if you're over... Hang on, no, hang on. If we're over BC, I don't need to check whether we're over AB because, you know, we made that check earlier, but it's after we've projected the point we've been making the check. So, okay. Just stay calm, don't lose your damn mind. So I need to copy basically all of this down to each one of these cases. Okay, so we're checking BC there, so okay, that's good. And then we need to check whether we're over... Yeah, we need to check whether this line is over AB. And if it is, we're at the intersection of BC and AB, so that's B. Okay, and now we need to check whether, because we're over BC, we check over whether we're over C. And if we are, we end up at C. Okay, that's good. I think. Hang on, that one's wrong. That one should be A. Why do developers do this kind of thing to themselves, man? Look, what is wrong? What is wrong with people? Okay, so we now need to check whether we're over... We need to check out whether we're over... So yeah, we've just checked we're over CA. We need to check whether we're over AB. Okay. And if we are, that means that we are at A, as we've gone from CA to AB. A is the common one. Right. Otherwise, we need to check whether we're over BC. Okay. And that's the difference to BC. And if we are, at that point, we've crossed CA and we've crossed BC, meaning we're at C. Okay. All right. Do you get all that? All right. Chances of this being perfect first time, actually 0. Okay, it's gone to the right corner. Let's reinstate the code that kind of like does a bit of a scan over it, you know, the thing that kind of like does a bit of a sort of like a drifting pattern, just to see if we can spot any other obvious discontinuities. And then once that's right, okay, it's sticking to the corner, very nice, very nice. Okay, let's give it, let's let it cook, let's let it go a bit wrong. Okay, it's sticking to that corner, that's good, that's very good. Okay, is it going to come to the front? I don't think it is. I think it might be slightly too far away. Okay, all right, let's adjust our kind of logic here to bring it back slightly. Let's bring it back to say -1. No, wait. This is in Blender space, so negative values are far away from the camera for some reason. Thank you, Blender. Oh, that was wrong. Okay, so which edge is that? We crossed at AB and we suddenly ended up at A. Oh no, it's all going wrong. Ah! No. Okay, let's check out that case first of all where AB suddenly goes to, so we're checking for a distance over AB, and for some reason, it then seems to think that it's over AC. Right, because it's going to point A. All right, why is it doing that? Let's just comment this out and verify that's the case. Yeah, if it does something different after I've removed that, then we know that's not the chunk of code responsible. No, it's still doing that. Okay, so there has to be another place in here that we're going to A. It's here. So this is when we start over CA and then get pushed onto A. So what's this doing here? This is getting the distance to AB, right? And for that, it's using the AB edge normal, which is fine. Ah, but it's using point C as the point of comparison, which isn't on that line. So it actually needs to be B. Aha. Let's just check the rest of these and make sure I didn't make the same mistake anywhere else. So that's point B on AB. That's point C on CA, that's point B on BC. Okay, that should be good. Oh, hallelujah. Okay, all right. Okay, let's just make sure it doesn't do anything else dumb. No, it's still doing something dumb. Okay, so it's crossing line BC, and it's intermittently thinking that it's at C. So we're going to have some logic in here somewhere that is, oops, no, don't use the global search, use the local search. So it's going to be one of these two. So let's comment that out, see if that improves our situation. Oh, come on, live. Right, and I'm praying that when I've actually fixed this kind of like perfect case triangle, come on. No, it wasn't that one. Okay. Do we have another case where it goes to C? Yes, we do. I'm praying that when we fixed all these issues with this kind of like, simple triangle, maybe I drop the whole mesh in and it'll just do exactly what we're expecting. Come on, come on. Nope, it's still going a bit mad. Okay, fine, yeah. All right, okay, so it's when it's crossing BC, it seems to think it's crossing CA. Now, that looks fine. Doesn't look wrong. I'm just going to comment this entire block out and see if it's coming from there. We're basically just trying to narrow down where the problem is, more than anything else. Because there's a lot of code. There's already a lot of code here, and it's getting quite difficult to spot where the issue might be coming from. So this should just fly straight over edge BC. Yeah, so yeah, the problem is in here somewhere. So we've got our distance to BC, and then we are then comparing it to AB using edge AB. That should be fine. Ah, we're using the wrong edge normal. There we go. Yeah. So we were using this normal to compare against this line, which is wrong. And it's probably just rounding error, that 50-50 chance of it being inside or outside the line. Okay, let's see if that works. Come on, work, live. Don't let me down, don't let me down. Okay, that looks good. That looks good. I now want to check this corner. So let's go into here and let's add 0.5 to it, which brings it closer to the camera because Blender is weird and backwards. Now, this looks like it went higher, it's just because it's closer to the camera. Okay, we're still not close enough, damn it. Okay, come on. Come on, silly string of doom. Show me it landing in that corner. Go on. Go on, go on, go on, go on, go on. Damn it! Oh no. Okay, now it has to land in that corner, right? There's no way it can miss. Come on. Okay. I think that worked. All right, okay. Let's revert this to how it was before with the full mesh. Okay. And let's do a build. Let's just watch for any ridiculous behavior. Come on. Okay, that's a bit weird, but seems to be working. Oh, it's projecting onto the surface. That was a bit weird. That's a bit weird. Oh, it's still not working. Oh my God. It might be an edge, I think, because we're so far off the edge. Let's take some copium and let's push it back up into the model and see if that looks any better. See how it looks kind of like, you know... No, it's still doing weird stuff. Why is it doing weird stuff? Oh no. Okay, the good news is this means it's probably a prioritization issue. Wait, that was still a weird thing it just did. What? Huh? Okay. All right, okay. Hello, second viewer. You are watching me have a complete and utter breakdown over triangles. This is meant to be finding the closest point on this mesh, and it's occasionally going wrong. Okay, all right, okay. So it looks like when it's below, it seems to be... Okay, when it's below, it doesn't seem to be handling the... It's still skipping over. Yeah, triangles are the enemy for sure. What was that? Why did it go all the way over there? That's weird. Hang on. Is that... Let's just triangulate this. And do an export, just so we're seeing the same triangles. Because there's a chance that my triangulator, my importer's triangulator, is slicing those quads into triangles slightly differently. Let's have a look. Yes, it is. Okay, with that in mind, why would it be jumping from there to there? Is this possibly... Oops. If it was over this, is there a chance you could think that's closer? Let's see if we can find that problem spot. It was around here, wasn't it? Oh, it's doing some weird stuff now. Oh my god. It's still doing just weird stuff. Okay, alright. So, let's see if we can figure out roughly where the point is. It was somewhere there. That was weird. Like, it's kind of underneath this triangle, right? So, let's find out where that point is, roughly. I'm very, very, very glad I'm able to just copy coordinates between Blender and the game engine. Makes it a lot easier to debug stuff. Make your own engine, he said. It'd be fun, he said. There's basically no chance this game even has a single completable scenario at this point by Halloween. Okay, it's not broken there. Let's move it left slightly. Gonna find the place at which it breaks. Okay, yeah, that's a point at which it's broken. Okay. So it seems to have attached itself to one of those two triangles. I can't quite tell which one right now. So let's remove all the other triangles in the mesh and see if we can figure out which one it's attaching itself to and why. So I think it should be under one of these two. So let's get rid of all of these and see whether it still does something weird. Oh, I think I can see why, actually. Oh, I can see why, and it's kind of actually expected functionality. So, right, what's happening is, our point is kind of, it's it's here, but it's at like 3.42. Right, so we can all agree it's underneath these two triangles, right? But I bet it's actually very slightly above this one. So technically it's above this one. So it's like, well, yeah, because in my kind of prioritization system, because one of the kind of problems I was trying to solve with this is, if you say got, two triangles like this and you have a point here and you're trying to figure out which kind of triangle it should be jumping to, it should be this one despite the fact this one's closer, right? But just because, if you kind of fell onto the triangle, it would be this one. And I'm trying to avoid encoding a direct, y-axis gravity in here because there's going to be cases in one of the games we'll make with this engine where there is no up. So, it's actually working as intended. It's working as intended, but not quite as I intended. I guess. I figure the best way to kind of is there any good way to handle this? Is there anything about this case, about this particular case? Let me verify this is what's happening. It will indeed only do exactly what I tell it to do, but the hard thing is trying to figure out the legalese that does exactly what I mean or want. Yeah, okay, it's definitely doing that. Okay. So let's have a look at this case. Let's see if there's anything about it that we can, obviously kind of sort of divine. Maybe we could have kind of like a... I was like, maybe we could have like a distance limit where... Okay, so one of the other cases I was considering, right, is kind of like this. Let's say you have a triangle here and you have a triangle here, right? You wouldn't expect to pop up into the room above. You'd expect to pop down to here, sort of, right? Yeah, if you place the monster kind of under this room, you'd kind of still expect it to go down, I think. I think you would. Or would you? Because let's say that it was very slightly outside the room like that. No, I think you'd still expect it to go that way. I think it should be based on distance and distance alone. Huh. Okay. All right. Okay. Let's just try get rid of all this specialist logic I put in, thinking it was going to improve things, and let's see if it actually improves it removing it. I wonder if closely we're starting to get into like an era of generative AI writing code. I wonder if it's going to be any better at just understanding what I want than this is. Get rid of all this. And we can get rid of one of these braces here. Okay, that should compile. And yeah, we set this, we never use it. Oh, wait. We should still be checking the distance. We should still be checking we've got the closest one. Yeah, we'll just steal that part of the code, put it back in. And then we'll put it back on the kind of like, I'm glad I visualized this, because otherwise I would have gone, yeah, it looks like it works. So yeah, now it's picking the closest point in general. So I'm just going to put all the other triangles back in. And then we're going to do the sweep again and see whether what it does makes any sense. I need to put the sweep back in. It's kind of weird. You know, I think that actually does what I want more than the bit with all the heuristics in it. That was a bit weird. Why did it jump around like that? Oh, what's it doing? What's it doing? Ah! At least it's not like doing weird stuff and like jumping across the map. Okay, right. So looks like we might have one more kind of like weird edge case to figure out, which is let's wait for it to kind of do that weird pop again. Make a note of which triangle it popped to, and then see if we can replicate it. Yeah, it looked like it popped to this triangle. Okay, let's see if we can just skip a few, like, see if we can skip to the bit that replicates the issue. Not quite, not quite. Let's put some numbers in here until it skips to the bit where it actually causes the issue. Come on. Okay, yeah, that'll do. Nearly there, nearly there. Actually, what was this the issue? Hang on, didn't it jump much further than that? Yeah, I think it did. Oh no. Ah! Losing my mind again. I'll jump to the bit where it glitches out and like selects random polygons from across the map. Go on, you know you want to, you know you want to. Thing is, I've done so many kind of like manipulations on the number of frames that have passed that I'm not entirely sure which number space I'm even working in at this point. So it looks like it's this triangle that's having a bit of an issue with. So let's just get rid of all the rest. Oh my God, this feature was supposed to save me time. It's costing me time. Ah! Right, so one of the things that could be kind of misleading here is that kind of the angles, it looked like it went, you know, it should have crossed this line, but it's 3D. It's a 3D line, so. What's our, yes, we're getting the square of the distance. It should be fine, we're only comparing squares to squares. That distance calculation looks like it should work. Yeah, I didn't see anything obviously wrong with that. Definitely recording it. Okay, This might be another one of these cases where it's actually not a bug and it's actually just, you know, the sort of data doing something that's not entirely obvious or intuitive. Let's just have another look at it. I just want to see if I can figure out like if this is a bug or not. So one of the things that might be a bit confusing here is that as a consequence of this being, you know, like slightly kind of wrinkled, it's not like it's not perfectly planar. It means that if you're looking at it from the side, what you might end up with is stuff like this. So you might have to say like, you know, triangles like this. Again, exaggerated example. But you end up kind of like, oh, actually, this is a bad example. Let's do a different exaggerated example. The actual kind of lines that it's kind of like checking against are kind of like this, right? They're kind of like smooth normals and they're kind of like averaged. And but then, say we're here, we're performing like distance checks from here to here. And, oh, okay, yeah. It's possible that when we're getting close to sort of like an edge, it's sort of, yeah, I can see what might be happening here. So we might end up with a case where the nearest point on this is actually slightly closer than the point directly under on this. So maybe that prioritization code wasn't entirely wrong, except maybe it should only have been prioritizing within walls, not necessarily hang on, let me just check something. If this extended out like this, and the point was here, you'd end up, this might explain some of the weird functionality we saw, because it would end up going, well, you know, project this point onto this triangle, okay, it's out of bounds, despite the fact that intuitively you'd think it'd be over the point. Okay. So, I'm pretty happy this code works at this point. I mean, it still doesn't always look right, but I think it's actually working. I think I'm just being confused by the kind of, you know, the sort of geometric reality. So let's just get rid of all this code to handle the all the code we were going to use to handle the well, prioritization. Oh yeah, this. This is something I mentioned last time. I looked it up and I was like, huh, I could have sworn they had some code to reverse transform a vertex so you can take, like, say, a point in the world and turn it into local space. I don't. No such thing really exists. What I'm going to have to do is store an inverse matrix for each entity, which a bit annoying, but I guess. I guess I'll have to do that. Okay, and this should still kind of work. Yeah, it still kind of works. It's picking like points on the mesh that are at least reasonable. Okay, what do I do next? What do I do next? Just gonna check something. That's good. What I do next is I commit this code because otherwise I will probably break it, forget that I've broken it. Yep, that looks good. That looks good. Yep, let's just commit all this before I break it. We're not committing this as this code is sort of debugging code. And we're also going to commit our vector math library. Calculate nearest points on nav meshes. Okay, so the next thing I kind of need to do is, sounds like it might be more complex, but it should be simple. Can you believe I'm saying that after that charade? So basically, you need to be able to take 2 points on the nav mesh, right? Assuming that I know which triangle they're in, and I need to be able to do collision with the edges of the nav mesh. So to kind of demonstrate what that is going to kind of look like, if you've got, like, say, bit of nav mesh like this, and we're kind of starting here and we're going this way. It needs to, actually, let's make a better example with like some, you know, some valid edge crossings before we get to that. So we're starting here and we're going here. It needs to go, okay, right, we've crossed that edge, fine. We've crossed that edge, fine. Oh, we've crossed this edge, but there's nothing there. Okay, kind of, oh, again, this isn't actually a great example. Something like that. Yeah, cross that edge, fine, cross that edge, fine, but then we want sliding collision with this. So we need to project this point onto this line. Hang on, I'm just thinking about this. Is that what we want to do? Oh, it's actually not, because then we end up actually moving more than we intended to. Okay. Thinking about it. What we'd ideally want to do is kind of... You don't want to stop dead, because then you get that annoying collision you had in a lot of early PlayStation 1 games where you bump into a wall and stop dead. And like it feels kind of like really kind of... It feels like all the walls are kind of like, you know, coated with kind of like tar and stuff. What I want it to do is slide a bit, but not go to like all the way, you know, just eyeballing what the perpendicular would be. Not doing something like that, because that'd be a bit much. It'd be, you know, like more distance than you originally went. I guess what you, or would it? Hang on. No, it actually wouldn't be more distance. It just feels like it is intuitively. Okay, is there a case in which that, I'm just like sort of like brainstorming ideas here for how collision work. I mean, like, it's a good idea to know what you're actually implementing before you try and implement it, right? So if I was to come at the wall that's nearly perpendicular, it would do that. So maybe the case is when a wall is like that, and I'm going to say there, then it would project onto, say, let's just extend this wall out. It would project onto roughly there. So again, it still wouldn't go any further. It just feels like it does. Okay, right. Okay, yeah. So let's just get this drawing back in. So we need to cross edges using the using these. Now let me just reset the game so we've got a working mouse cursor. We need to cross the edges using these normals to detect when we're doing that, and keep track of which triangle we're in until we reach an edge that we can't cross, in which case we project the endpoint onto the, we almost kind of like start a new search, sort of. You know, we basically take this line of travel and we turn it into this line of travel. And because then we actually need to keep crossing edges until we reach, until we reach an edge that we can't cross. We should probably also have a limit on how many edges you can cross. So, you know, if you try and cross, say, more than, I don't know, 30 edges in a single iteration, that might be a sign of like some, you know, float imprecision causing like an infinite loop. So we need to work around that as well. Okay, so let's make something vaguely like this in Blender. So yeah, rotate this edge. And get rid of that, get rid of that. Rotate this edge, get rid of that. And rotate that edge. I'm thinking that while you'd have a starting triangle number, you wouldn't have a destination one, because you might be trying to go something that's out of bounds, which is actually fine to try. Fine for like the player or an AI character to try and leave bounds. It's just so we need to be able to constrain them once they do. So yeah, we're going to be starting from here and we're going to be working our way over there. I'm going to try and keep this relatively planar. Try. The other thing is, should we be colliding with the ground? Oh, okay, so actually one thing I have just thought of is that when you actually reach here, because we have like edge crossing points, it's kind of ambiguous when you hit this vertex as to whether you should be going. Actually, it's not, because this triangle knows nothing about this triangle. I was thinking like, you know, if you're like crossing a vertex, well, you're not crossing an edge at that point, right? But as far as kind of the nav mesh is concerned, it's just an edge from here to here and an edge from here to here. So that should work out fine. It does mean you're going to have basically a bit of a weird, you know, even though you're only crossing one edge visually, it means you're crossing two numerically, but that should be fine. So, another thing I should probably think about is, hang on. I was thinking, like, am I ever going to want a function that allows me to kind of like trace from outside the nav mesh and like hit a triangle on it? I can't think of a case where I'd need to do that, because even if I was like, you know, say clicking on the world, I'd want to be clicking on the visible geometry and then finding the nearest point on the nav mesh and navigating to that. Yeah, so we've got our nearest point on the nav mesh function. We're about to write our kind of like ray tracing one we can use to do collision. And then the only thing left to do after that is to do the kind of like, you know, flood fill search to find the shortest path from a point on the nav mesh to another point on the nav mesh. Okay. I was actually thinking about that because one of the things is you can just cross, you know, you can count like nav mesh edge crossings to get an idea of how far away you are. But that does mean that if you had like big and small triangles, which is definitely possible, and I'll probably even encourage in the kind of like engine design, it means that you can end up with some pretty wrong estimates. And like, yeah, don't really want to do any distance calculations during a flood fill. Maybe I could kind of like, you know, cache the sort of like average distance between the midpoints of the edges, so we know if we're going from that edge to that edge, how much it's going to cost. Yeah. All right. That's enough. That's enough waffle, I think. So let's try and implement this ray trace function. At least start it, because we're probably not going to get that far of it today. So I think this can go directly into the nav mesh. Yes, it can. Yeah, the only reason we put the closest thing in here is that we need to be able to compare cross. Oh, okay, right. So yeah, the reason I put this, because I've got the idea of a nav mesh on its own, right, which is kind of like separate from the scene. It's basically just a Just realized I've lost something on my desk. Oh, there it is. Okay. The reason I had this kind of like as you have a nav mesh, which is kind of like, it's almost kind of like the model as it's exported from Blender. And then you have a nav mesh component that connects it to an entity in the scene. And I moved this code to find the closest nav mesh from the nav mesh to the nav mesh component. The reason being that I had all this like additional logic in here to like try and go, well, you know, prioritize nav meshes you're above over ones you're below, which you can't really do that across nav mesh if you've got multiple in the scene. However, I'm no longer doing any of that logic because I found it actually introduced strange behavior. So I could actually theoretically move this into the navigation mesh. I'll do that another time though. So, we're going to call this sliding collision. Yeah, we'll just call it that. And for the sake of kind of like, my sanity and, well, performance and stuff, we're actually going to be considering that anything we're colliding with the edges of the nav mesh is just a point. We're not considering like radii or anything like that on, you know, we're not considering like this to be, you know, like a sphere. And the reason for that is, it means that if we're, say, doing collision, we only have to consider the triangle we're in, because it's impossible for us to actually, say, collide with, you know, if you were in this triangle, to give an example, and you're approaching this edge, sorry, if you're in this triangle and you're approaching this edge, you would never have to consider this, you know, this edge of this triangle, because you're a point. You can't possibly be big enough to hit that. Okay, so sliding collision. So we have a navigation mesh. That's nice and easy. I'm thinking we actually make it so all the coordinates are local to the nav mesh. That would make a lot of sense. Perform sliding collision of a point moving through a navigation. I have to type navigation mesh because if I type nav mesh, the spell checker shouts at me. Navigation mesh to collide with. The point in the navigation mesh's local space. The location of the point at the start of its current motion in the navigation mesh's local space. There we go. And we have the destination as well, so that's where it's going. And then we need yeah, we need like a result. And what this is going to, we need to sort of like say that this can't be the same as these two inputs. No, maybe, no, we'll make it so it can be. Why not? And because I'm feeling particularly generous today, perhaps we'll actually return a bool saying whether or not it collided. Thinking about it, you would actually want to know separately whether it's colliding with walls or the floor, and the reason for that is, and oh, maybe you want a callback as well to know when it's collided with things, so you can like make sound effects and like you can like, I'm like, because you might want, for example, you know, like say footstep sounds to play while you're traveling along the floor, but not while you're, say, sliding along a wall. So we'd need separate kind of callbacks for those. Well, sort of variables for those. Let's make a new kind of like enum sort style thing, but to flags enum. Okay, describes the collisions which occurred with a navigation mesh. Okay, so yeah, bit flags which describe the so we're going to have one for collided with the triangle itself and one for collided with the edges. All right, okay, that should be good. All right, okay, that's good. And then we can follow that up with, we need to then import that into here and actually return it. And I should probably actually specify here, rather than the result, the location of the point following any collisions. And return the types of collisions which occurred. I'm also going to need some more functionality with this in the future. Like, I'd like a sort of like a sticky mode where kind of like things can't leave the surface of the nav mesh. So that's a weird thing that can kind of happen in my kind of like sort of not a nav mesh, is that if you've got like, say, looking side on like this, it's actually possible for things to rise above the nav mesh. Which means you could, say, have a collision like this where it never actually hits like an edge like this looking down, but it does kind of slide off there like that, which would kind of end up sort of there-ish. So yeah, a lot of things can happen with this sliding collision system. What do I call this type again? There you go. Something nice and wordy. It's always nice and wordy around here. We're incapable of writing short names in general. So we've got origin, destination, and these should both be constant, and I have a result, and that should do it, I think. I do need to import this, so I'm going to do that up here. And now we just need to implement this, the easy bit. Right, for just kind of like the sort of like beginning of this, we're basically going to implement a kind of like a dummy kind of implementation that does nothing really, just basically writes the input to the output. So yeah, so it returns 0, saying no collisions occurred, and I'm going to bring in that vector math library I was working on last time. And it's not in video, it's in the root. And I'm just going to copy from destination to the result, and there's 3 axes on this. Okay, and then in a kind of like advanced routine, we need to yeah, rather than using the closest, we're going to use this new function. Oh, I've just realized I've missed one a really, really obvious argument to this that needs to be there, which is we need to tell it which triangle it's currently in. Yeah, we don't really want it guessing, given we've seen that our sort of, the heuristic we're using to figure out which triangle you're closest to is a bit not great. I'm just trying to think of a good way to say it that's charitable and stuff. Okay, did I actually export this from Blender? Let's just do that now. Okay, we've got a kind of like snake puzzle trap thing. We've got a start point. Let's put our end point like, say, let's make it so that, let's make it work for it a bit. Let's make it so that it'll kind of slide a bit up there. Yeah, that should be good. So it should end up slightly, it shouldn't end up kind of like parallel with the sort of like line of motion. It should end up kind of like pushed slightly up the wall. So yeah, actually, I'm still going to use the closest thing. What I'm going to use it for is I'm going to use it to kind of like find the initial triangle, and then I can use that information to do the sliding collision. Okay. So rather than using this, we're going to use this point here. Again, so glad I put the effort in earlier to make it so like I could just copy coordinates directly from Blender to this. I mean, it'd be a nightmare doing these transformations, not knowing whether I've got them right or not. Yeah, so we're going to get our destination, and we're going to initialize that from this. So again, we've got a known good destination point. And then we need to actually call into our ray tracing function. Sort of. It's sort of ray tracing. It's kind of a bit disingenuous to call it ray tracing, but it sort of is. So I didn't import the nav mesh into here. I'm going to need it. That's the wrong file. Not the script. There it is. There's our nav mesh importer. Pop it into here. We're going to want the navigation mesh itself, not the components we used to attach it to the entity model. And yeah, we've got a slight collision. Okay. We can then give it the mesh we've imported. We can give it the triangle that we found by searching for the closest point. We can give it our origin point. We can ignore the one that came back from the closest point. We're not really using it for anything. And then give it a destination point. We give it where we're going, and then we give it somewhere to store the result. And we should then be able to draw some lines. I'm overloading so many words here. Okay, so we've got a yellow to magenta line, which is the direction in the motion that it's trying to do. And let's do something else. Let's do green to Green to white, that'll probably do. That's a color combination we haven't used yet. And this will show us where it ends up. Oh, it didn't like that. Oh yeah, there shouldn't be any F on there. Okay, and we're going to do a parallel build because we've changed the header file, meaning it's going to recompile every single C file. Oh, and it blew up. But because we did a parallel build, I can't see the error. Oh yeah. Great job, me. Naming two completely different things the same thing. Oh, we had another error there. And, oh yeah, I changed one of these, but not the other. That's right, yeah, I gave one of them the triangle, not the other. And we can make that const. Very good. Go. I'm going to guess I brought in the index header here. Yes, I have. Okay, and this is just saying that we're not using any of these parameters yet. That's actually expected because this is kind of like just dummied out. So let's just get this kind of working. Not using any of this yet. Let's just get it drawing a line on the map and just make sure that everything lines up with what we're expecting. Oh, it's still not having it. Why isn't it having it? Oh, hang on, I've done something really dumb. I haven't updated the header's guard name. So it's, I probably brought in like the alignment header somewhere else. It's just going, oh yeah, I don't need to bring this in because I've already brought this in. Okay, that's building. Let's make it in parallel. Go, 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 go. Build. Okay, yeah, so there we go. We've got that point and going from there to there. And as you can see, it's kind of not doing any collision at all yet. So, don't know how much further we're going to get with this today. Probably got another 20 minutes. What we need to do is, first of all, we need to let's make our own local variable for this. And we're going to make our own local variable for the current origin and current destination, because we're going to be kind of like sort of distorting the line as we're kind of traveling along here. It was previously from here to here, and it's going to change from here to here. Maybe I should also make it so when you cross one of these, yeah, I'll do that. Now, one of the things I need to take into account actually is rounding error, because if we hit this line here and we project the start and end of the line onto this point here, what we're going to end up with is a 50-50 chance of them being inside or outside the triangle due to rounding error. So we actually need to like bias it, like maybe move it a centimeter or something inside the triangle so that it's definitely within the lines. What I should probably do actually is put a not edge lengths. Yeah, I should probably put a thing in here to detect extremely small triangles and go, level designer, what are you doing? This is probably not going to work due to rounding error. Okay. So we're going to have an iteration count. So let's go to something like 16. It's probably going to be enough iterations. It's unlikely we're going to be crossing more triangles than that in a single frame. Let's copy over our origin and destination. Okay, and let's start. Just took a second for that to kind of like underline. Let's start doing some horrendous math. So we need to, first of all, we need to get the triangle out of the nav mesh that we're currently in and look at its properties. So that's in the triangles array, funnily enough. Who saw that coming? Oh, you see that? I wrote a $sign. I've been writing too much PHP lately. It's bad for you. So let's get our triangle out. And the other thing I should probably start doing is actually tracking these collision types while we're going. So yeah, I'm going to start that off at 0. And then whenever we encounter a collision, we're going to kind of like fix that there. So as a special case, thinking about it, I was thinking about surface collisions because they're actually a bit different. They can't possibly cross a nav mesh triangle, but they can occur. I was thinking about this. We actually want to compare all 3 edges of the triangle, find out which one it's going to hit first, if any, and also look at the surface of the triangle, because if it hits the surface before it hits an edge, then you know it needs adjusting. Okay. Right. So which vertices do we need? We only need 2 of them, realistically speaking, kind of like before. There's actually going to be a lot of similarities between this and the code we just wrote to do with finding the nearest triangle. So yeah. So we need to compare the current destination to each of the 3 edges and see which ones it's over. And if we need to find the closest one that it's over, and then yeah, kind of react to that, I guess. Now, one of the things we need to be careful with here, actually, is it's entirely possible that, let me just check, is this possible? Let's say that we had a triangle with very, very mismatched lengths like that. Is it possible that we'll collide with a triangle? Hang on, because like, trying to figure out what the kind of like best sort of. So what, when it comes to detecting like a collision with an edge and like how far along we are, we basically need to take the destination point, right? Project it onto the plane of the edge. Hang on. Do we? Is that true? You've written code before to do like a collision between a plane and a line. You remember how it works. You're not losing your mind. Oh my god, I'm losing my mind. Okay, let's just try and work this out again, because I've forgotten how you do this. So yeah, we have a start and an end point. And, okay, right, okay. So you project, hang on. You get the difference between the start point and a point on the plane. You then multiply that by the edge normal. So you dot product that with the normal to get the kind of like distance of that point, of the start point away from the edge of the triangle. You do the same with this to get kind of like the distance from there to there. At that point, if the end point is over the line, you know how far along the line it was by the proportion between these two. So if it's like if it was like 3 above and 2 below, you know that it occurred 3/5 of the way along the line. So let's do that. Let's use that as an approach. Okay, so hang on, I'm thinking. Yes, it hurts. Yeah, I think just write this out and see what happens. So as before, we subtract the current origin from, in this case, I'm going to use B, and we've got 3 axes, and we write the difference. We then perform a dot product between that difference, and actually it's the destination we care about. We care about the destination, not the origin, because we can use that to figure out if we're over the line at all, and if not, we skip calculating how far along we are. So at that point we're looking at AB normal. And if the distance outside is greater than 0, then we know that we're over the line. And at that point, we do something kind of similar where we take the origin point. Yep, okay, this is all making sense to me now. And we dot product that with the edge normal. Okay, so now we know how far out we are and how far in we started. And at that point, we can say that the closest is definitely the first edge, and distance to the closest is going to be distance outside, subtract the distance inside. Hang on, it's getting confusing because our distance inside is actually negative. So if we do the distance inside divide by the distance outside, inside, take the distance outside, what we end up with there is we've got, like, say, in this case, it'd be like -3 divided by -3 subtract 2. So it'd be -3 divided by 5, which gets us 3/5. Because it kind of like negates a negation of a negative. Man, brains were not meant to do math, were they? They were not. Okay, so now we are going to do the same thing. Oh, I might make a second. Yeah. Yeah, I'm gonna make more variables for this because I could see myself reusing them later on. Oh, I actually want to keep that. Yeah, I actually want to. It's the B difference, not necessarily the AB difference. There's a thing here. I guess. Hang on. I might still need. Yeah, I'm going to need the inside difference as well in some cases. I'm trying to think here which case is more likely, because, like, so I need to calculate both the difference between the point inside and the point outside, right? If I'm like, if I've got, like, say, you know, vertex B here, and I've got a line like crossing here, and let's say this is, for the sake of argument, AB, and this is CB. I need to first of all calculate, the difference between this point and this point, so I can know if it's over AB or if it's over CB. But I only have to calculate this point if I detect that this is over either one of these two lines. But I'll need the same value twice. I'll need it whether it's over this line or this line. If I assume that most of the time, you think about it, you'll be crossing one of these maybe once every 10 frames. It's actually more efficient to calculate this value twice than it is to calculate it. It's more efficient to calculate it twice sometimes than it is to calculate it once every time. Right? I suppose. That seems plausible to me anyway. So that's what I'm going to do. To hell with the rules. Now, but there is a case. Hang on, is there a case in which I would... Yes, so when it actually comes to collision, I would actually be projecting that point onto the line. So I'd actually be using it 3 times, not 2. Yeah, at that point, I think I am going to keep it, actually. I think I am going to calculate it each time. Okay, so next up, we only need to do another, we only need to do another dot product, really, before we can calculate if it's over the next line. So that ends up being dead simple. It just ends up being that. And this time looking at BC normal. And again, BC normal. And we then check if closest is and distance. Just calculate what the next one's going to be. So yeah, that should work. And then we unfortunately do need to calculate another one of these for line CA because that doesn't have vertex B on it. So we need to calculate another pair of these. Not the end of the world, not the end of the world. All right, okay. I'm glad I didn't try and write this as a loop. This would have been confusing as heck to write as a loop. I could theoretically have looped over, like edges A, B, B, C, and CA, but I don't think that would have helped much with complexity here. Okay, that should be good to go. Find all references to BC and change them over to CA. Should be dead easy. Got a few variable names I need to update. Probably introduced a whole bunch of bugs by doing this, isn't it fun? Oh yeah, and then I need to take the outside difference here. And this needs to be the C outside difference, C inside difference. That should be good. Okay. We've got a lot of missing variables, that's kind of fine. We just haven't sort of read them out yet. Next thing we need to do is we need to check whether the ray is going to intersect with the floor, and if so, we need to Oh, damn it. Do I need to? Yeah, I was thinking like, is there a case where I can say like, just say project the movement against the floor and then just carry on, assuming that, so if this is the floor of the triangle and this is kind of like the edge of it, assuming that the kind of like, edges were always going to be perpendicular, yes, you could, but because we have the cases where say that you've got like a curve like this, not really actually where you hit, where you collide with this could actually change where you hit this wall. So I do actually need to do like an iteration for hitting the floor. That's kind of annoying, but not the end of the world, I suppose. So we do still have we can actually reuse this again for the kind of like floor collision. So let's do that now. And we can use any of the vertices for this because they're all on the surface. So that should be fine. Oh, this is still called BC. That doesn't bode well. It means I didn't do a good job of replacing things. Yeah, I really didn't. Half of these still say BC. Man, that last line effect bites hard. Now, we're not currently accounting for things that start outside of the triangle, and that should be fine, generally speaking. That shouldn't really, that shouldn't really be possible. Okay, so at this point, we need a switch statement where we look at the closest thing, and if it's zero, then we didn't collide with anything at all. And this is our best case. It means we can just return the collision type straight away, and we don't have to worry any further about this. It's all good. It's all Gucci. Nothing went wrong with our collision check. Oh, we do also need to just copy over the. We need to copy the current destination to the result. Yeah, that's what we need to do. And if it's 1, we know we hit edge AB. If it's 2, we know we hit edge BC. If it's 3, we know that we hit edge CA. Oh, I've just spotted the bug with this. That's backwards. And if it's 4, we hit the surface. And if there's anything else, that can't happen. I was tempted to put like an error handler in there, but I'm like, that can't happen. We've just specified everything that can happen. Okay, so this should be if we don't have a closest hit, or we're closer. It shouldn't be if we've hit something and we're closer. It should be if we don't have a closest hit and we're closer. So if we don't have a closest hit or we're closer, I can't even say it. Okay. So in theory, these are actually all the same thing. They're all basically taking a point and a plane and projecting the start and end onto it and looping back around. So what I'm actually going to do is I'm actually going to move this into its own case. No, actually, I'll leave it in there. I'll leave them there. I'll just have these variables up front and never use them. That's fine. Because like, well, if I'm declaring variables up here, they're going to be set by all 4 of these. I don't really want them kind of like for hit this, but it's probably not going to do anything. Collided point, which is going to be that, and collided normal, which is going to be that. And then, actually, I could probably make them pointers, and rather than copying the data around, I can rather than copying the data around, I can instead just point them to the appropriate information. And they're going to be, let's have a look, const pointer. I had to look this up yesterday because I couldn't remember what the syntax was. So we want a pointer that we can change to something that we can't. Okay, it's that one. Because there's this really confusing thing with like C, where it's kind of like const char C means that it's a pointer you can change to something you can't. Char, star const is a pointer to something that you can change, but you can't change the pointer itself. So you can't point it to something else, but you can change the thing it you can follow it and then change whatever you find. And then you can also have, it's a pointer, you can't change where it points, and you can't edit what it points to when you get there. So that's the one we actually want. So in the case of this, we want collided point equals B, because we'll have B at that point, and it'll be on edge AB, and the collided normal will be, I think I've got like a, AB normal. It's abnormal. Ah dear. And then we've got on BC, we've got point B, and we've got C on CA. And then we can use any point because it's a surface, and we're using the surface normal. Okay, at that point, we need to, we need to linearly interpolate between the start and end point to find the new origin point. So I'm actually going to add a new vector helper for that, because it's very, very common you do linear interpolation, right? It happens all the time. So that's going to be a, this might be something we end up having like multiple overloads out. Maybe you have kind of like a vector alpha value, but in this case, let's go to our math header and make sure we use the same terminology from there. Linearly interpolates between two vectors using a scalar. The vector to linearly interpolate from, the vector to linearly to, oops, what's it right there? Interpolate, yeah. And we're also going to need the unit interval. And I'm just going to steal that because that's just probably better written than anything I can come up with today. So yeah, read-only inputs and a pointer we can't change, the values we can for the output, and we're going to rename these to be consistent. And it's not a multiply, it's a linear interpolation. And this again should be pretty easy to write, as there is an optimization we can do with this actually, in that because we're doing multiple axes, we can actually calculate the inverse unit interval. So that'd be 1.0 take unit interval. So now we've got kind of like, helps you name it, doesn't it? We can then iterate over the axes, and we can do this. Okay, that should do what we want. So we now have the progress along the line, so we can linearly interpolate the start point. Yep, that works. So we've got the current origin to the current destination and the distance to surface. Yeah, distance to closest, there we go. And then we've got 3 axes on our vertex, and We're overwriting our current origin. And then we need to project the endpoint onto the, yeah, we need to project the endpoint onto the plane. Okay, yeah, we can do that. So I think we should have the, yeah, we already have the outside difference, so we can use that up here. We might not need the point actually. Okay, so now we have, I'm running out of space to doodle things, aren't I? We have our edge here, we have our start point, our end point. We've now projected this onto here, so now we need to project onto here, so we need to... Oh, actually, we don't need the outside difference, we need the outside distance. That's a different thing. So that's a, I think I'm storing that. Yeah, distance outside, there it is. And yeah, I don't think I need the collided point. We'll find out though. Dead easy. I'll be happy if I get this working this morning. I'm yeah, not crossing my fingers because like I'm overrunning a bit, but it might be possible. Yeah, it could happen. Okay, so, oh, the other thing I'm going to want to do is I'm going to want to actually, just going to make a note of this before I forget about it. Shuffle us slightly inside the triangle. Oh, something else I've just thought of actually is it's possible that we'll move entirely along the plane. So I need to put, yeah, I'm definitely not going to get this done today. I'm just going to make some notes on things I need to check for. Let's do check for here. Yeah, because it's entirely possible that we're actually moving perfectly in line with the plane that we're kind of like trying to collide with. In which case, I need to think about the best way to handle that. Yeah. Yeah, so what that might mean is, to give another example, if I've got this here and I've got a start point and an end point, that perfectly, and it is possible you could actually start outside the triangle now that I think about it. Yeah, so imagine these are, you know, perfectly parallel. That would mean that, you know, if we're trying to figure out where this line kind of intersected this, it never does. Yeah, I need to think about that. And that's not the pointer, that's fine. And that shouldn't be const, that's fine. Yeah, so now we know how far outside we are, so now we need to multiply our normal. Yeah, okay. Collided normal with our distance outside. Yep. And then we've got 3 axes and we're writing it to the multiplied normal. So now we've got a line, got a start point, end point, draw a line between them. We now have this. So now we just subtract that from this and it should get us back onto the line. At that point, we start from the current destination, we subtract the multiplied normal, and we've got 3 x's, and we write it back to the current destination. Right, so next up we've got to implement this slight shuffle to get us back inside the triangle, because we are very slightly outside the triangle. So I'm just going to define a constant here. Push inside triangle, I guess I call it. It's going to be a very small number. Yeah, very, in that case, that's a centimeter. Let's go for a tenth of a centimeter. It's just so that we don't get this thing, we end up riding the line and generating a bunch of collisions along the way. We're very slightly inside it now. So for this is dead simple. We just add that push inside triangle like that. Dead easy. For this, let's we're just going to have to do another small little, multiply this by this. And we're just going to have to subtract. Yeah, we have to do another subtract. That's kind of annoying, but that's just how it is. Yeah, so basically going to be just, once we've kind of like projected the start point onto the line, we're then going to push it very slightly away from the edge so it can't overlap it. Okay. So there's things we know are wrong with this. We know we're missing like division by 0 checks here and here and here. We are now pushing slightly inside the triangle to make sure that we're handling correctly when we're pushed inside the triangle. So what that means is, if I have a triangle like this, right? And let's say that, we had a collision from here to here, we're right by the vertex. And for the sake of, exaggeration, let's say that our kind of push factor, we push back to the line and we want to push slightly more and we end up pushing to here. We end up actually overshooting the triangle and ending outside of it. And it's possible that the start point could also do the same. So let's say that the push factor was more like that. It's possible we could end up like that, where we end up with the start and the end outside the triangle, because we tried to collide with an edge. Yeah, I wish I had a good solution to that, to be honest. But I don't. Oh well. I guess I could do another check immediately after pushing it back inside the triangle and make sure that didn't cross any edges. But the question is, what do I do if it does? Because, if it's like an edge that, if it's an edge that we could cross, that's actually kind of fine for the destination, but not for the origin. So I guess what should actually happen, hang on. Okay, right, so yeah. If the origin is now outside of the triangle, force it in. Try to think of the best way to handle that, really, because if you had, like, say, a massive triangle and this like thing happened like all the way down here, I mean, how would you know where a safe point is? I mean, like, you'd know that this point would be safe, be right in the middle of the triangle. How could that be unsafe? But then you've ended up like massively distorting the line. Oh, hang on, I've just realized something else. We don't actually output the triangle we've ended up in. Oops. Oh, no. And also, we're not actually advancing this to the next triangle. I just realized that as well. Current origin is going to be... oh, hang on. I just realized something else really stupid I've done here. I'm not handling neighbors. If I'm crossing into a, if I'm, say, in this situation here, I'm treating this edge like it doesn't have a neighbor and I'm just going to collide with it, which isn't right. That's a bit of an oops, isn't it? Okay, I'm going to define these variables and see what the hell happens. Why not? Because while I'm not expecting it to work, I do have an expected outcome. So we'll see if that happens. So we're going to pull out the... hang on. Just remember what order these go in. That's right. So we should need B and C, and the surface normal would be good. And we're going to need edge AB, which is AB normal, which is edge normals 0. And we're going to need BC and CA. And just for consistency, let's order these the same as the orders in the logic. Oh, wait, I wrote that wrong. I was like, why isn't that changing from red to like a nice healthy blue? Add those missing parameters, specifying how many axes are on in the... Performance-wise, I'm assuming the compiler is smart enough to see that, because I've got like linked home optimizations turned on very aggressively. It should be able to see this as a constant value being passed in, right? And it should be able to unroll this loop. If it can't, I mean, like, we'll figure it out. Okay, this is saying we're not using these. Are we not using these? Oh, yeah, I'm using the wrong variable. But yeah, collided point we're not using at all. So I guess what I could do for the origin point, I kind of want to keep it inside the triangle, I guess. Here's a thought. What if I never update the origin point? Is that a good idea? Could that ever have unintended consequences? Let's just sort of workshop this. Let's say that, like, I then did sliding collision to there. And then, hang on. Let's just scribble this away. I'm gonna need a bigger eraser than this. Okay. Let's say that you went from there to there and you collided, and then we ended up pushing your line all the way up there. And we changed the destination to there, and we ended up doing a collision sort of from there to there. Yeah, that would kind of break things. Yeah, I can't do that. I need to reproject the start point. Yeah, you'd end up crossing the line there, which is weird. Yeah, that's not good. That won't work. It built. Should we see what it did? Should we see what we've won? Yep, that's wrong. And you know what? I'm out of time. So let's leave that there, shall we? Thank you very much for watching. Hope you have a great weekend, and I'll see you another time.